circuits here. So in topic 5.2, we'll start talking about inductors and resistance and about energy changes there. We will talk about that. It is also just like these 2 pages. After that, the last topic is like electromagnetism, which is the Maxwell's equations. For these Maxwell equations, for you to understand, you need to remember some things from Gauss law. You remember the Ampere's loop? We used to make a loop to find out magnetic field. Do you remember Biot-Savart law?
Hello.
Then I
Oh
told you there's
shit.
another way to find magnetic field. There are 2 ways. One is Biot-Savart law, one is the Ampere's loop. You just go and
Yeah.
make a loop, and you used to have whatever current is there inside, and you multiply that with mu naught, and you get the magnetic field easily. Those equations that you have done before, one related to the Gauss law, one related to the Ampere's circuital law, these laws, they combine to make some 4 Maxwell's equations. And these 4 Maxwell's equations we will do at the end. And it's just a summary of the whole your AP physics. What I'm trying to say here is this topic 5.3, it is a summary of whatever you studied from the beginning of the course till today. Got it? After this topic, we are done with the your unit 5, the whole course, for example. Then we can go and start solving the questions. Clear?
Yes, miss.
Okay. So let's start with a small recap here. So we started with magnetic flux, right? Let me open what we did last time. Okay. Okay. Flux. You can see my screen?
Yes, miss.
No. No, which screen can you see? You are seeing the PDF, right?
Yeah, we can see the PDF.
Yeah, no, I'm writing somewhere. I want to share something. Okay, now you can see I'm writing?
Yeah.
Okay. So I told you in the last classes that flux is a general term, and this term is used to say that what is the rate of something flowing through an area. Okay. So when you say electrical flux, it means how many electrical field lines are passing through a given area. If I say magnetic flux, it means how many magnetic field lines are passing through a given area. So flux is just like the rate of flow. Okay. The term flux is in general rate of flow. Even if you go to these pipelines and all these things, they talk about flux a lot, this term. Anyways, so for magnetic flux, I told you in previous classes, it depends on 3 things. If there is a coil and there is some magnetic field here, okay, B, this is magnetic field line. If I increase the B, if I increase the magnetic field, will the flux change?
Yes.
Right. So number 1 is I can change B to change the flux. Change the flux. Second thing I told you was I can change the area. For example, this is a circular loop, okay, a conducting loop. Now, I am keeping it in such a way that all the field lines B are passing through the loop. But if I rotate this coil here, if I rotate it like this, wait. For example, this is your loop. At the beginning, this is your coil, okay? But after some time, if I rotate it and I make it like this, do you think the magnetic field lines passing through the coil will be the same?
No, different area, right?
No, they're changing, right? See, the orientation, it depends on the orientation.
Oh, the
Just
angle,
think of a,
yes.
yes, the angle. So number 2 is, it if the angle changes, angle between the area and magnetic field. Area vector and the magnetic field vector. If this changes, the area and magnetic field vector, if the area between them changes, the flux will change. This will cause change in flux.
Yes.
Okay, change in flux. Last thing, number 3. Oh my God. Okay, number 3 is, now, for example, you have some magnetic field lines here. Now you have a small area here. This flux and same magnetic fields, but a bigger area. There is a change in flux or no?
No.
If I change the area, more lines will pass through it.
Yes, it
But
will.
if the area is small, only few lines will be able to pass through it. Correct?
Yes,
So
ma'am.
if I change the area of the coil, it means that the magnetic flux will change, correct? Bigger area, more flux. Less area, less flux, right? So the third thing is the area. When you change the area, there is change in flux. I'm going to write change in flux in short way. This is called change in flux. Correct? So there are three things that are contributing to change in flux. So when I say what is the formula of flux, we say B dot A. Why do we say B dot A? Because we know that the dot product between two vectors means BA cosine of angle between them, right?
Yes, miss.
So there are three things which can change the flux. One is the magnetic field, one is the area, and one is the angle between the magnetic field and the area vector. Correct? Do you remember this part?
Yes, miss.
Okay. Now let's go to the next part. The next part in which I was talking to you was, okay, one part before I go to the next. This whole thing that we are doing right now, this is about the magnetic flux. After this, I'm going to talk to you about Faraday's law, then I'm going to talk to you about Lenz's law, and then we will go to the next part. So remember the area vector. For example, this is your surface. This one. Area vector. Okay, area vector. Let's say this area is 25 meters square, just for an example. So if your area is 25 meters square here, the direction of the area vector is always perpendicular to this plane. It means that the area vector will be pointing out of the screen. Got it? This is the plane, right? This is the plane, the coloring. I want to make a vector which is perpendicular to this plane. Got it?
Yes, miss.
I want to make a vector which is perpendicular to this plane. So if I put my pen in such a way that it is pointing towards me out of the screen, it is going to be perpendicular to this plane.
Yes.
That is my area vector. So area vector is always perpendicular to the plane. Remember that part. So this is the first part that I did with you guys in the last few days when we started this chapter. Then I started doing with you about Faraday's law. Faraday's law. Oh, I didn't record it. Is anyone recording it?
Recording in progress.
Yes, I'm recording it.
Okay. Faraday's law. In Faraday's law, I told you that the rate of change of flux is equal to the induced EMF, which means how much flux is being changed in a given time. That will tell you how much EMF is induced. You know what is an EMF, right? Potential difference. So we said that rate of change of flux. We say that whenever there is change of flux, okay, and then the rate of change of flux means in how much time it is changing. For example, I told you if you have a coil and you put a magnetic bar close to it, if you move this magnetic bar close to the coil and far away from it, close to it and far away. If you move it very fast, like if you bring close to it and move it back very fast, if the motion is very fast, the change of flux is very fast, is more. If you do it very slowly, you hold a magnetic bar and you bring it close to the coil slowly, and then push it back slowly, then the change of flux, the induced EMF will be very small. Okay, so the rate of change of flux is equal to induced EMF. which I told you that we can write it in an equation form in such a way that if I ask you what is the EMF average, you will say how much flux was changed in how much time. Okay, which means flux final minus flux initial divided by delta T. This is the average EMF, right? Then I told you that the EMF instantaneous, if you want to know how much EMF was there exactly at 2 seconds. Okay, EMF instantaneous. Okay, it will be equal to d phi by dt. By the way, we always put this one here because sometimes you get answers in negative, and negative means because of the direction. So always take the modulus value. Okay. Is it clear, guys?
Yes.
Okay. This is the EMF. Now, EMF means the induced potential difference, right? Now, the induced potential difference or induced EMF can be there even if it is not a coil, even if it is a normal wire, okay? If it's not a closed loop. But current cannot flow if the your circuit is not closed. So current will only flow if there is a loop there. For a normal straight wire, current will not be induced. Clear? So then we want to find how much current is induced. Can you tell me what is the formula of current in terms of voltage and resistance? Guys, can you tell me what is the formula of current in terms of voltage and resistance?
Voltage over resistance.
Yes, voltage over resistance. Do you remember this? We know that the voltage is the potential difference, right? EMF. So we can write this as EMF divided by R, correct? We just found EMF at here. You see, we have found EMF here. EMF average and EMF instantaneous. So it depends on the question. If they are asking you about what is the average current, if they ask you what is the average current, use the EMF average, this one. Delta phi by delta T into 1 over R. Are you getting me? And if I asked you, like if the question asked you, what is the instantaneous current? Then you're going to use d phi by dt 1 over R. Is this clear? Clear, guys?
Yes, Miss, it's clear.
Yes.
Okay. All of this, whatever I'm doing right now on screen, we have done this. This was our lecture number 2 on Faraday's law. Then we went to lecture number 3, which was Lenz's law. After this, I went to Lenz's law directly. And we have done some questions in each class about these topics. Lenz's law. The Lenz's law is little bit like, you can say it's a little bit challenging to understand. So in Lenz's law, you have to use your brain like actively. What happens is that Lenz's law says that the direction of the induced current, actually Lenz's law, the reason of Lenz's law is to find the direction of the current. We say that whenever there is change in flux, there is induced EMF and induced current, correct, in a coil. But we want to find out the direction of the current. Okay, we know that there is a coil and we know that there is some flux changing and induced current is there. But what is the direction of that current? How do we know that? That we get to know from Lenz's law. Okay, Lenz's law is going to tell you what is the direction. And what is this law saying? That this law says that the direction of the induced current is always such that it opposes the cause producing it. Let me write this down, that the direction These things are very important, by the way, what I'm doing right now. Direction of induced current is such that it always opposes the cause producing it. What does that mean now? I gave lots of examples. Is there anyone who remembered those examples? Anyone who can explain what is Lenz's law with an example? Do anyone remember what is Lenz's law? Guys, hello. Guys, we did lots of examples. Is anyone active here? Hello.
I think Ubaida knows this.
Nobody knows it.
اشخص جدي.
I'm
Yes,
asking you
yes, I
about the
think,
Lenz law. We did the Lenz law. This is just like 2 lines which I wrote here, okay? We did lots of examples to explain what is it. And I told you it's a little bit challenging and all that in the class as well. So do anyone of you remember what is Lenz law and give me just one example? Oh, or at least explain me what I wrote here.
Is it like does it relate to the solenoid that we took?
No. The solenoid was the last chapter. This is a new unit. This is totally different. Remember, guys, listen. Do you remember that I told you that the direction of current produced in a coil is such that it was trying to always go opposite to the reason that is producing it. There's the reason, right? What is the reason that is producing it? Change in flux, right? And change in flux comes from 3 basic reasons that I just explained here. Either it is the magnetic field, or the area is increasing or decreasing, or the angle is increasing or decreasing. Something is changing, right? Some change is there going on there. That change is producing induced EMF and induced current. Now, induced current's direction will be such that it will try to oppose this change. Do you want me to give an example? Okay, let me give you an example. Okay. For example, you have some magnetic field lines going on like this. And then let's say that there is a coil here. Okay. I am saying that the magnetic field is increasing. B is increasing. I will just give you one example because I cannot go through this lecture again. Okay. Let's say that the magnetic field is increasing. Now my question is, if the magnetic field is increasing, okay, which side is the magnetic field? Into the board or out of the board? Guys, is the magnetic field inside or out of the screen or in the screen? What does this cross represent?
Neither.
So into the screen.
Into the screen, right?
Into the screen.
Yes, the magnetic field is into the screen. This cross means it is going inside the screen. Now I am saying that the magnetic field is increasing. This, what I wrote in green color, is that the magnetic field is increasing. This is in the question. Okay. You are supposed to tell me what will be the direction of the current. Will it be clockwise or will it be anti-clockwise? Okay. Now, if B is increasing, okay, what will it do? It will change the flux, correct or wrong?
Yes.
Yes.
Okay. The flux will change. Flux is changes. 1. Flux change. Okay, now if the flux is changing, my second question is, what is the opposing thing? The magnetic field is going inside the board and it is increasing. If I want to oppose this cause, what should I do? Which side should I produce the magnetic field to oppose this change?
Opposite direction.
opposite direction, right? I should produce a magnetic field which is out of the board, right? Because this magnetic field is going inside the board. The change which is inducing the current, which induce the current, this is little bit like you need to understand it well. The magnetic field is changing. I am changing the magnetic field, which is causing the induced current. So what is the main cause which is doing everything? The change in magnetic field, right? And the change in magnetic field is such that it is increasing into the board. I will write here, into the screen. Into the screen. Okay. So magnetic field is increasing such that it is increasing into the screen. Now I want to oppose this change. So if I want to oppose this change, what will I do to oppose this change? I will try to produce a magnetic field. B will be produced such that it should come out of the screen to cancel that effect, right? Are you getting my point or not?
Yes, miss.
Okay. Now tell me, in which direction should the current move in this loop to produce magnetic field out of the screen?
Counterclockwise?
Counterclockwise, right? You remember that right-hand rule?
Yeah.
Like if the current is flowing like this and then like this, just curl your hand fingers in the direction of the current. Curl the fingers, the four fingers of your right hand, in such a way that it is moving anti-clockwise as I'm showing you in the screen. So your thumb will point out of the screen, correct? So the magnetic field produced because of the induced current is opposing the change.
Yes, miss.
The magnetic field is being produced because of the induced current. The induced current is moving anti-clockwise. This induced current is producing a magnetic field which is going out of the screen. But initially, the magnetic field which is given in the question is increasing and it is going into the screen. We are trying to oppose it. So we are producing a magnetic field which is going out of the screen. The induced current will make the magnetic field such that it will go out of the screen. This is Lenz's law. And I have just given you one example. There are lots of examples. Like now I told you B is increasing. I can also say B is decreasing. Got it? We can have other examples also. We did these examples in the class. I will give you one more example, one small example, okay? Is this part clear or you don't want any more examples? Is this clear?
Yes, miss, it's clear.
You don't want any other example with the magnetic bar or something? You'll be able to do that in the exam?
We hope.
Guys, all of you will be able to do this part?
Yes.
Okay. So let me talk to you about. Okay, let me give you another law. Just let me give you another law. If you have magnetic bars with you, okay, let's say there is like this, a magnetic bar is there. This is north and this is south, okay? And there is a coil here. If I bring the magnetic bar close to the coil or away from the coil, there will be change in the flux, right? And there will be induced EMF and there will be induced current. If you want to find out the direction of induced current in a loop, if you want to find out the direction of induced current in this loop, due to the magnetic bar that I'm bringing close to it or away from it, one of the things that will be very useful for you is, I'm writing here, write it down in your notebooks, okay? This is very important what I'm telling you. Look, S. Can you see S here? that I'm writing an S here. Look for the direction. What is the direction I made? Is it clockwise or anti-clockwise?
Clockwise.
Clockwise. So whenever there is clockwise direction current, you will say that the side that you are seeing or the side that you are facing, from which side you are saying that it is clockwise, that side is producing south pole. Okay. And this S, why I made it like this, just for you to remember that whenever you write this S like this, you will remember that it is clockwise. South pole is always clockwise. Now, if it is north pole, look, north pole. I'm just writing N in little bit fancy way. This is down and this is up. This is which direction now? Clockwise or anti-clockwise?
Anti-clockwise.
Look, this is clockwise
This is anti-clockwise.
or anti-clockwise, right? So whenever it is anti-clockwise, you can say it is north pole. This is anti. And this is clockwise. Okay. I will give you a very, very small example about this one. 1 minute. I think my screen is a little bit stuck here. Okay. No, better. Okay, let me give you a small example. This is North Pole and this is South Pole. Okay. And there is a small conducting loop here. Okay. Now, carefully tell me, if I move this magnetic bar away from the loop, this is the motion. Okay. If I move this bar away, like I'm taking it up, away from the coil wants the change such that it will oppose the change, correct? South pole is going away, correct?
Yes.
It will try to attract the south pole. This is the opposite reaction to whatever is happening.
Yes.
So what will it try to produce
North
here
pole.
on this side? It will
South
try to
pole.
produce north pole, right? To attract it back. Come back. Why are you going away? Come back. This is the opposing, right? The
Yeah.
magnetic bar is going away. The south pole is going away from the loop. It will try to make north pole here, to bring it back, to attract it, to create the magnetic force of attraction and bring it back down. And I told you for the north pole, what is the direction of the current, anti-clockwise or clockwise?
Anti-clockwise.
Anti-clockwise. So you will know that the direction here is going to be anti-clockwise. Is this clear now?
Yes.
Got it or no?
Yes, miss.
See, if you look at this loop from above, if you look from here, let's say your eyes is here from this side, it will look like anti-clockwise. But if you see at the same loop from down, it will be clockwise, correct? You getting me or no?
Yes, miss.
Okay. So this will be south pole down and north pole on the at the above. Okay, so we are done with 3 topics, which we did in the last few classes. It is just a recap. We did the induced EMF. We did the flux, how the flux changes. It changes if the magnetic field changes, if the area changes, if the angle changes. Then we talked about the Faraday's law. Faraday's law says that the EMF is equal, the EMF induced in a loop because of changing flux is equal to uh, change in flux divided by time, change in time, or d phi by dt. This is Faraday's law. Then the Lenz law tells you the direction. Lenz law says that the direction of current will be always such that it will always oppose the change causing it. Clear? This part is clear, guys?
Yes.
Okay. Now I want to do 2 questions about this topic with you. 2 like exam questions. And then I want to go to the new topic. So we are running out of time. I want to send you a new link. There is only 3 minutes left for this meeting. I will send you a new link and you can join with the new link. Okay. Okay. So I'm going to end this one and I'm going to send a new link.
I am lost. I am lost. حزن. What is a solenoid? Solenoid. Oh, okay, خلاص never mind.
Okay, guys. Am I audible?
Recording in progress.
Oh, yes, miss.
Yes.
Okay. Let's try problems about this. One of the MCQ questions that you can see is this one. What is the acceleration of magnet in free fall? It's writing a little bit slow. My pen. So here is the magnet. This is south pole. This is north pole. And it is going down like this. And then they show a coil here. And then they give you 3 options. Option A is saying, is the acceleration is equal to gravity? You know that the anything that's going down, like falling down, it's under free fall, it has 9.8 meter per second square acceleration. You know that, right?
Yes.
Right, you studied that 9.8 meter per second square is the acceleration of anything that is falling down.
Yes, Miss, we
The
know
Earth
it.
is pulling
Yeah, of course.
the gravity. Okay. So one of the options says that the acceleration will be equal to that 9.8. The option number 2 says that the acceleration will be less than g. Option number C says acceleration is going to be greater than g. Greater than g, less than g. Okay. And then there's another option D, let's say not determined or something. Now carefully tell me which option is correct. Use your minds and tell me that when it is going down, okay, the Earth is pulling it down. It is coming down. The North Pole is coming down. What will be the reaction of the coil's induced current? According to Lenz's law, the Lenz law says it is always opposite, right? So what do you think will happen here? Which direction will the current be induced in this coil? What will that current do? Can you tell me, guys, quickly? Guys, no one is going to answer this question. It's very easy. We just did it now.
Will it be going, Miss, clockwise direction?
You are saying that it will go in the clockwise direction. What's the explanation for that?
No, wait. Miss, will it be going counterclockwise because the N is down and the charge is going downwards?
The end, the North Pole is coming close to it. It wants to throw it back, correct?
Yes.
The North Pole is coming down. The coil wants to throw this magnetic bar away from it because it is coming close to it. It is always going to oppose it. So if the North Pole is coming down and I want to push it back, which pole should I produce here, north or south,
South.
to push it back?
Okay, no mind.
Guys,
North.
which,
North.
if there is north here, then only it will
Be pushed back.
what we call repel it, right?
Yes.
Okay. So because north is coming close, we want to repel it and we want to throw it back. So there will be north pole produced on this side. So when the north pole is produced, which direction will be the current now? North pole means,
Right. Up.
I told you, north pole.
Counterclockwise.
Counterclockwise. So this is the direction of the current now. Okay. This is just like I just gave you this one for no reason. You don't need the direction, by the way, in this question. You just need to know that this coil will try to throw it back. So it is coming down with G, and there is one force coming from the coil which will oppose its motion and it will try to push it back, right? So tell me that the net acceleration will be greater than G or less than G?
Greater than G.
Less.
Less than G, right?
كيف how?
Because the opposing one, the induced current which is opposing it, it is throwing it back. There's G which is pulling it down, and there is one force which is pulling it back. So when you do the plus and minus, it will be less than G, correct? Because it is in opposite direction. So this is the answer, B. Is it clear, guys, or is there any doubt there? Any doubt?
No, it's clear.
Okay. Now another question. This is not an MCQ question, but a normal question. My question is, find the induced EMF and the induced current and the total charge. Now there is a question about total charge. Did I talk about charge until now? I did not talk about anything. But let's see how we are going to find it. And total charge that flows from time t is equal to 0 to time t is equal to t naught. Guys, as I told you that my screen is responding very late. I don't want to write each and everything. Can you remember the question? It is number 1, induced EMF, induced current, and total charge. Okay?
Okay, miss.
3 parts: induced EMF, induced current, and total charge. Clear? I'm going to just make the diagram here to make it clear. The question. So there is magnetic field. Let me try to do it here. Maybe it will be better. Yeah. And this is a coil here. It has a radius r. Okay, can you hear me at least, guys? Because no one is talking, so I feel like I'm talking to myself. Can you hear me?
Yes, miss, we can hear you.
Hello?
Yes, miss, we can hear you.
Yes, Miss. We can hear you.
Okay. Now, the question is that the magnetic field here is given as B is equal to B naught T square. Okay, this is the magnetic field given. And they are saying that the time goes from T is equal to 0 to T is equal to T naught. This is the time change. Okay. Now you are supposed to find out the induced EMF and the induced current. How do you find the induced EMF? What is the formula of induced EMF? Part A, induced EMF.
Miss, the average
Nobody
or the
knows how to
instant?
find the induced EMF?
Miss, the average or the instant?
Okay. So what is the formula of induced EMF? To find the average. Correct, you're saying correct, but
It's delta flux over delta time.
okay, delta flux over delta
Time.
time.
Yeah.
Correct? And what is flux? How do we find flux? What is the formula of flux?
BA or BA cosine.
Very good. So we know that the flux is equal to B dot A. Correct? Now you want to find the flux initially and the flux finally, right? B dot A means BA cosine theta. Now we know that at the beginning, what is your B? B naught T square. And what is your area? Pi r square, correct?
Yeah.
And cosine of angle is going to give you cosine of 0 because the magnetic field is going into the board and the area vector is also going in the same direction because it is perpendicular to the plane, right?
Yes, miss.
Okay. So cosine of, let's say it is cosine of 0, okay, which will give you 1. So this will become B naught T square pi r square. Clear? Now here I want to find delta phi means phi final minus phi initial divided by time. Okay. Now my second question is, what is phi final, the flux final and flux initial from this formula? You know that flux T is equal to 0, say it is going from T is equal to 0 to T is equal to T naught. So what will be your flux final and flux initial? Just substitute the value of T in the equation, guys. Substitute the value of T here. Okay. B naught. Instead of T square, for the final, I will write T naught square, correct?
Yes.
Okay. Pi r square minus. And then for pi initial, I'm going to write T is equal to 0. I will substitute T is equal to 0 here, which will make it 0, correct? Here.
Yes.
Divided by delta T. From what is delta T? T naught minus 0, which is T naught, correct?
Yes, miss.
Guys. Okay. Which is T naught. So what is your induced EMF? B naught, T naught, pi r square. Clear?
Yes, miss.
Yes.
This is the induced EMF. Now, if they ask you, what is what's called induced current? Average, sorry. This is for the average. Again, let's do induced EMF instantaneous first. Okay, if I do induced EMF instantaneous now, what will that be? D phi by dt, correct? This is your d phi. Now, do you know how to do d phi by dt from here? You know the differentiation, guys?
Yes, we شو اسمه derive it, right?
Okay. Yeah, derivation d phi by dt. This one, just do for me d phi by dt. What will be the answer? Guys, you don't know how to do the differentiation of t square? Seriously? Just bring this 2 down and it will become like this 2 b naught t pi r square. From this t square, it will become 2t, right?
Yes, miss.
Okay. Yeah, from the t square, it becomes 2t when you're going to differentiate it with respect to time. So this is the answer for induced EMF instantaneous if you're finding. Okay. Now let's find the induced current. And I will do instantaneous first. Okay, to find induced current, we know that we are just going to take this EMF and just divide it by the resistance, right? You remember? So I will say it will be 2 B naught T pi R square divided by the resistance R. EMF divided by the resistance is going to give me the current. Correct or not?
Yes,
And
miss.
same thing here, if you want to find the induced current average, if I want to find I average, I will take this value of induced EMF and divide it by R. All of this is clear?
Yes.
Okay, now comes the part which is little bit important for you to understand, and it is something that they are expecting that you should know it yourself, you know. In the questions, they expect that the students should know it themselves. When they ask you to find out the charge, okay, when they're asking you to find out the charge for them, there is a derivation for it, first of all. Can I erase all of this? Or
Yes,
should
miss.
I, wait a minute. Wait, okay, I will just put a new slide so that we don't miss anything. Okay. I told you that I is equal to dq. You know this, right? I is equal to dq by dt. You have done this. Change in charge divided by time is equal to current. You have done this? Guys, you have done this? Oh my God. Have you done this? I is equal to q divided by t.
Yes, miss. Yeah.
Okay. Now I'm saying that because we know that I is equal to dq by dt, can I say that my dq is equal to I dt? Just taking dt on the other side here.
Yes, miss.
Okay. In the previous slide here, we already found out our induced current instantaneous, which is here, this one. We found it, right? So can I just say that my dq is equal to 2 b naught. I'm just writing the value of I. 2 b naught t pi r square divided by r dot dt. Correct?
Yes.
Okay. To find the total charge, I'm just telling you the way how you're going to do it. Because from your previous knowledge, you know that I is equal to dq by dt. You're just going to take the dt on the other side. Now you're going to integrate both sides. Okay. Here you want total charge. So you're integrating here. And here you are going to integrate with respect to time. And we know that the time flows from t is equal to 0 to t naught. Correct? It's given in the question. So here when you integrate for the total charge, you will get total charge q. Here, whatever is not related to time, you can take it out of the integration, thinking of it as a constant. 2 is a constant, b naught is a constant, pi is a constant, r square, which is the radius square, is a constant, resistance is a constant. Only thing that will be left inside is the t, right? So I'm going to take everything out. 2 b naught pi r square divided by r, and what is left inside is from 0 to t naught. What are you going to integrate? T dot dt. Clear? Any doubts still here? Now, when you want to integrate t dot dt, which you know like this one, x dot dx, you know it becomes x squared by 2, right?
Yes, yes, miss. We know
Hmm.
basic integration.
Yeah, so it is going to be 2 b naught pi r square over r, and this one will become t square by 2. From where to where? From t naught to 0.
0.
Yeah, so this will become 2 b naught pi r square r. We don't need to write the 0 part. We know it will go to 0. So when I go do t square by 2, it will become t naught square by 2. Correct?
Yes.
So this 2 and this 2 will just cancel out with each other. And that's the answer. B naught pi r square t naught square by r. The small r is the radius and the capital R is the resistance. Any doubts still here?
No, miss, no.
Okay.
Oh,
Now
it's all
let's go
clear.
back here. And let's go back here and now try to understand what will be the direction of current in this coil. According to the equation given in the question, this is the equation given in the question. This one. Okay. This is given in the question. According to the equation, can you tell me when the time increases, what happens to the magnetic field? It increases or decreases? B naught t square means when time is 1, when time is 1 second, it will become B is equal to B naught 1 square, which is B naught. When time becomes 2 seconds, it will become 2 square, which becomes 4 B naught, right?
Right,
When
miss.
time goes to 3 seconds, it will become 9 B naught, 9 times B naught. So when the time increases, what happens to the magnetic field?
It increases.
It is increasing, right? Now, according to my Lenz's law, I should produce current in my coil in such a way that it should oppose this change. The magnetic field is increasing into the screen. I want to produce a magnetic field which will oppose this change. So which side should my magnetic field go?
Out of the screen.
According to the induced current, it should go out of the board, right? So to
Counterclockwise.
produce a magnetic field which is going out of the board, what should be the direction of the induced current in this red coil here?
Counterclockwise.
Counterclockwise, right?
Yes.
All of you are understanding? Anyone has a doubt here?
No, it's
So it
all
will
clear.
counterclockwise. It will go like this, and then the current will come out of the screen. Okay. Now, I did this part with you in a way which is a little bit long, and you should know it very well how to find total charge from direct. We have not spoken about charge at all in this lesson, but you should know from your own previous knowledge that because current is equal to dq by dt, so I will do this, this, that. But there is another way of doing the same question, but and that way is much easier. So I will try to tell you that way also. So if you see any question in exam, you can use any method that you like. I told you that the current is equal to dq by dt, right? Dq by dt, correct? But I
Yes.
also told you that current is equal to d phi by dt 1 over r. Remember?
Yes.
So this is also current, this is also current. Can I equate both of them? Can I say that this is equal to this?
Yes, you
Because
can,
both
miss.
of them are giving me current. So I will say dq by dt is equal to d phi by dt 1 over r. Both sides I have dt. Can I cancel them? Yes, I can
Yes.
cancel them. So I can say that my dq is equal to d phi by r. Right?
Wait, miss.
So my change in charge is equal to my change in phi over r. This is another way of doing it. You can, what I'm trying to say here is that if you don't have current, but you have the flux, you can still get the charge.
Okay.
This is very important. And the derivation that I did there is also very important. Uh, Please note down, okay?
Okay, miss.
I think I'm not even recording. Yeah, I'm recording. Okay. This is important, and this part is also important that you should know that you have to do some integration to get the answer. Okay, so this is the first part. Now I'm going to talk to you about one small part about this same topic, which is induced EMF due to rotating coil. If you have a coil, okay, and you rotate the coil inside a magnetic field, because of the rotation, the angle is going to change. The angle between the area and the magnetic field, right?
Mm-hmm.
And because the angle, when it will change, it will create a change in flux. And because of that change in flux, there will be an induced EMF. So we will just do a one problem and that will be very understandable for you. Let me do one question. Another question. So if you have magnetic field lines like this, they are into the board or out of the board? Out of the board. Then you have a coil here. It has, sorry, it has a radius r. The radius r. Now, what I'm trying to say here is that this is the axis of rotation, which means it is rotating like this. Got it? Moving like this, rotating inside the magnetic field. Now, as it rotates, the magnetic field lines passing through this coil will change, which means there is a change in flux. We are now asked in the question, find the average induced EMF, induced EMF and current if it rotates 60 degrees in 2 seconds. Now, this is the coil, it is rotating. In 2 seconds, it rotated by an angle of 60 degrees. Now, you are given this information. You are supposed to tell me what is the average EMF and what is the average current. This is the question. To find the average EMF, first of all, we need to know the flux, right? What is the flux? We know that flux is equal to B dot A, which is equal to B A cosine of angle, right?
Yes.
Okay. Now, B is B, where the B given in the question, the magnetic field. But the area is going to be pi, let's make it smaller, pi r square. Now, what is the cosine of angle? What is the cosine of angle at this point?
It goes from 0 to 60, right?
Yes, it is going from 0 to 60. So for flux initial and flux final, it is going to be different, right?
Yes.
So let's keep it like this for now. Let's keep it like this for now, that this is our flux. And then let's do separately for final and initial. So my flux final is equal to B pi r square cosine 60, correct? And cosine of 60 is half. So it will become B pi r square by 2. Correct or wrong?
Yes, miss.
And then my flux initial is equal to, we know that initially the angle is 0 and cosine of 0 gives me 1. So initially my flux is going to be b pi r square.
Yes.
Okay. And they are asking me to find average EMF. So you know that the average EMF is going to be delta phi by delta t, which is equal to phi final minus phi initial, which divided by delta t, which is time t. And how much will that become?
B pi r
Uh,
squared cosine 60 over 2 I mean.
oh, wait. Cosine 60, we solve it. Cosine 60 is equal to half. This is the answer you get.
Yes, miss. My bad.
So, and by the way, do you remember I told you we always take the modulus. Do not take any negative values, okay? Okay, so let's take this one minus this one. It will give me b pi r square divided by 2. Anything divided by half of it will give you half of it back, right? 1 minus half is half, correct?
Yes.
Yes.
Yeah, so b pi r square minus b pi r square divided by 2 will give me b pi r square divided by 2.
Yes, miss.
Okay, we got this as change in flux, but did I do the delta t?
No, we didn't.
Did I do the delta t?
We do it over delta t, right?
We want, yeah, and what is the time given?
2 seconds.
So it will be multiplied by 2. So this will become b pi r square by 4. This is the answer for EMF. Clear? We did the EMF, average EMF, right? Now, if you were asked to find the current, what will it be?
Current.
Hmm. Guys, from EMF, how do you get the current?
شو اسمه نسيت.
EMF times 1 over R.
Yeah, we divide by the resistance. That's it. You take this value and divide it by the resistance. That's it. Nothing else. Nothing difficult there. Okay. So, average current. Do you want a break? Are you tired?
No, I'm so good.
Okay. So average current is equal to this value B pi R square divided by 4 and then capital R, which is the resistance. Please, like you should know in your mind that this R, capital R is the resistance. The small r I'm using is for the radius of the coil. So this is the average current and this is the average EMF. Any doubts here in this question?
No, miss, no.
No.
Everything is clear until here. Now let's go to one last question. After this, we have 8 minutes. Let's quickly do it in 8 minutes and then I will keep another class for after Maghrib, okay?
Okay, miss.
You guys are free after Maghrib?
Miss, no, we're not free. Can we do it tomorrow if we can do it after Maghrib?
No. Tomorrow, definitely there is already a class. But what I was thinking is that before going to school, let's finish this part, the inductors. That's why I wanted to do it today, like another class. Because until now, we have only done like some problems. There's one problem still left from this part only. We haven't even touched the inductors. So tomorrow's class won't be enough. Or what we can do is tomorrow's class, we can keep it a little bit like longer, like maybe 2-3 hours. Tell me, what do you want?
شباب سيف يا أخي speak up.
Safe mind that I
Won't be free after Maghrib.
After Maghrib?
Yeah, we know we won't have time. We're
We won't
we're
have
gonna be
time.
out of the house.
شباب شو عندكم؟
Okay.
Can we do it tomorrow, miss? Like 2-3 hours?
I told you it's up to you. You guys can decide like how you want it. Tomorrow,
I don't mind
but
tomorrow's option. I don't know about the others.
so
Yeah, I
tomorrow
don't
we
mind
start
either.
at the same time, 12:30.
Yeah, okay, miss.
Okay. So we start at 12:30, then we take one class, then I will give you a 10 minutes break after like 1.5 hour or 1 hour 15 minutes. I will give you 15 minutes break and then we come back and join again. Something like this. Not like
Okay.
after Maghrib or like this, no. Like in one sitting we will finish it all.
Okay, miss.
Okay. Miss, can you assign some things on College Board, like some assignments and progress checks?
Sorry, come again. I didn't understand.
On College Board, I saw that you're the teacher. So can you
Mhm.
assign some like progress checks or assignments for the lessons, like the previous lessons, like Unit 3, 4, and 5?
Okay, for now, what I will do is I will assign you from what I am doing right now, from this topic, so that
Okay.
you practice what we are doing. But once we complete, as I told you, we are not left with a lot of topics. We will finish, inshallah, all of this in like 4 or 5 lessons more. So once we finish all of this, we are going to go through all the previous topics and then revisions and all those stuff. Once we start doing revision, then I will start assigning that. But because now I think you will not remember those things very well.
Mm-hmm.
So better we revise, and whatever we revise in the class, we do problems related to that will be helpful for you.
Okay.
Okay. So let's do one more question here. Question number 2. Now we have only few minutes left. Let's be very quick. So there's a magnetic field like this. Okay, and there's a coil like this. And then this coil is rotating like this with an angular velocity W. Do you know what is angular velocity? When something is moving in rotating, okay, there's revolutions going on, we use a term called angular velocity, which is W. So W here is equal to 300 revolutions per minute. Okay. And they have given you in the question that the B is equal to 4 into 10 raised to power minus 2 Tesla. And the area of the coil is also given, that the area of coil is equal to 25 centimeter square. And what else they have given? Let's say that the resistance is 4 ohms. This is all given in the question. Okay. Now they ask you find the induced EMF in the coil, but this time it's different. Okay. Look, find induced EMF in the coil, but part A says, part 1 says in half turn, and B part says in full turn. Oh, find average induced EMF. This is average. Now, let us be very, very, very careful. When you have this coil and it rotates or it revolves, it is moving around its own axis and it takes one whole turn, what is the flux final minus flux initial, this term? When it takes the full turn. Guys, please try to use your brains little bit and tell me what will happen if with this term. The flux final and the flux initial, will it be the same or not in full turn? Something is like this. It moves and comes back to the same position.
Yes, miss, it will be the
So the
same.
final and initial will be the same, right?
Yes.
So if any time in an exam you see a question where you have a coil or something or anything and they ask for one whole turn and you're asked for finding the induced average EMF, you know that this term will directly go to 0. This answer will be 0. Why? Because flux final and the flux initial are going to be the equal. Because it took full turn, it came back to its original position. But this does not mean that the instantaneous flux is 0. There's a difference. When you say an average induced EMF, it means that, okay, when it was going half of it, maybe it was positive. When it is coming back, maybe it is negative. So when you do the plus and minus, it goes to 0. You understand? That is the average induced EMF. But if I ask you what is happening exactly at that point when it has turned one complete turn, after one complete turn, what is the exact EMF? It will not be 0. These are two different things, average EMF and instantaneous EMF. Am I making it clear?
yes, miss.
So, okay, let's do the half turn. You will understand a little bit better. Let's do the half turn. So for the half turn, let's do flux initial. So flux initial is going to be B dot A. We know that BA cosine angle. And we know at the beginning that the angle between the area vector and the magnetic field vector is 0. So we will say BA cosine 0, which is equal to BA. But when you do the flux final, I'm doing part A now, okay? For the half turn, okay? Now, in half turn, when you do BA cosine angle, what will be the cosine of angle? Will it be cos 0 now? When the coil moved half of it, not the whole turn, half of the turn, what will be the angle now
60
in
again?
half turn? See, initially the angle is 0. When the coil took a half turn, he just rotated
90?
half of it. 180, yeah, very good. BA cosine 180. And cosine of 180 is negative 1. So it will be minus BA. Now you understand why in full turn it became 0? Because when you do the plus and minus, it will go to 0. One is positive work and one is the negative flux. You get it? Okay. Now in half turn, when I ask you to give me the EMF, average EMF, it will be equal to flux final minus flux initial divided by delta T. You already found the flux final and flux initial. It is minus BA minus BA. Correct?
Yes.
Minus BA minus BA divided by delta T. Now, this is the part which you have to understand. Delta T, we said that there are 300 revolutions in 1 minute.
يا أخي ذكر هذا.